bigger than local dimensions. Whole. Here. Here this reference point. Okay, so this is the result we want to prove right now. But here we are not settled our original question yet. We don't know when this is going to complete. But I'm trying to show that if this is complete, then this will hold. The local dimensions will hold. And in order to prove this, we have to use this compactness result. Now the consequence here, these consequences, and is going to be used in the proof. But the codimension, finite codimension, this is a consequence from the first consequence, so it's not going to touch here. So this is a byproduct. It's a byproduct. The key is here. This is. Okay. So we're going to now. So suppose I have to. Suppose not. So I'm using the contribution method. Okay. Now, so suppose I have a Q here, but there is no small neighborhood for such that this guy hold the local unit is hold. So what does it mean? Suppose not. What is the consequence of suppose not? This means that you have two sequences of potential closing to Q, but they are different but they carry the same distribution. They're not right. So this means that suppose now then they exist. So two sequences potential Q M1 and Q M2. So Q M1, Q M2, they're both close to approach to Q. Okay? While here the space is C1. We're all thinking about this potentially C1. Okay? And with the Q M1 not equal to M2, but this particular map is equal. Okay? I'll have that. So now we go to the identity. So then the identity tells us that integration of Qm1 minus Qm2, then the U1, 1m, U2, and dx equals 0. So where B and I is a solution to this problem. Okay. Right. Okay. So here, now in order to continue, the idea is you have to take the limit, right? But the thing is that you cannot take the limit immediately, directly from this identity, because otherwise, here you end up with 0. So that identity disappears, you don't get any information. Okay. So what we're going to pay attention. So the idea is I'm going to choose this solution appropriately. Okay, appropriate. So what we're trying to do is for any two solutions, V1, V2, which corresponds to the Schrödinger equation with the potential Q. That's the reference potential. Okay. Okay. I take any arbitrary solution to this Schrödinger equation. Okay. Now, once I take these two solutions, the reason I'm taking these two solutions is that I'm going to consider the PQQ. PQQ is formed by all the product. All the product of solution coming from this potential, right? Mm-hmm. So eventually I have to go back to this potential. So what we're trying to do is, first, I'm going to pick up a product. So the product is formed by B1, B2, satisfied this equations, okay? Then from these two solutions, I'm going to construct the corresponding solution here. So we're going to construct Vn1, Vn2 to be the solution with this Schrodinger equation. And the boundary value Vmi is equal to Vi. So I fix a pair of solutions for the potential Q that use the corresponding boundary value to determine the sequence of solution here. Vm1, Vm2. That's carries the same boundary value. Okay. So now here we are dealing with multiple notations, but the connection is this. Okay? And now we're going to use some approximation theory, but here I'll skip the detail. Then one can show. We can show following, that you see that the Vn solution carries the same boundary data as the Vi, right? And also the potential Qm will close to Q. So when m goes to infinity, you can see you will expect that Vmi will approach to the Vi because they carry the same boundary data and the coefficient, the potential close to the reference potential. Okay, so from here we can see the Vmi will approach to the Vi. Okay, so in C2. And in the sequence space, okay. So here, why we can show that? So it relies on some standard elliptic estimate. So if we have time, or if you're interested, you can take a look at some paper. I mean, it's a very regular argument, but it's kind of tedious because repeating the elliptic regularity theory. Now, this one is understandable because these carry the same boundary data, and the equation for this carry the coefficient very close to coefficient for this solution. So that's why approximation is expected. Okay, so then you can see that this will imply that the Vm1, Vm2 will approach to V1, V2 in L2. While here, the C2 is much higher than L2, so use the embedding theorem, you can or solve it before that you can see that this conversion can be in L2. Okay. Okay, so this is an intermediate point, which I need. Okay. So now let's return to this identity here. Okay. So you can see that if I take n goes to infinity, okay, so this portion will approach to this V2, right? But the things you cannot take the limit immediately here because otherwise this guy will approach to 0. Okay. Then if you go this directly, you don't get anything, right? You get a trivial identity. Okay, so what we're trying to do here is I'm going to find the Fm to be equal to the Q and 1 minus Q and 2 divided by the norm. Q and 1 minus Q and 2. Okay. So I know here at the very beginning, after suppose not, I have the two sequences, and they're not equal. They're not equal. So therefore, if I divide this, so this norm is non-zero, so therefore I can, so this function is right. So this function said like this condition f m L2. Okay. Right? So it's for n. So this, in particular, if you think about the Fm set is bounded. Okay, so now it's time to use the compactness result. Now compactness result is this, right? This. Now here, so then we have to pay more attention to the things that's connected to C. Now what is C involved here? That's a constant. The C actually involves like the dimension or dimension equal to omega. It also involves Q C1. Okay. Yeah, I think at some point we have to add one more remark. So when while we're working on this, eventually you see the main thing we want to work is. Now suppose this one is replaced by another thing, Q1 and Q2. Suppose they're not equal, okay? Then this thing is still defined, right? This is the L set. And still you can think about the perpendicular subset. And in this case, they will still having the same kind of compactness result. Exactly the same proof. Okay. The only difference is that in this case, then this potential is not just single thing. You know both potential, like C omega Q1, C1, and Q2, or C2, something like this. Okay. That's exactly the same thing. Now, here, so from here, now if I return to here, you can see this guy, using this notation, you're going to have the Fm is perpendicular to U and is Vn1, Vn2, dx equals 0, right? Okay. So this means that for the potential Qn1 and Qn2, the Fm turns out to be perpendicular to the it's perpendicular to the set. Right? You understand what I'm talking about? Because this one is coming from this here. From here. And I use Q for this difference to define the Fm. So therefore you can see that in this case, actually, if you look at here, you can see this Fm will perpendicular to any product here. Any product here. So from here, you can see that the assumption of this compactness theorem is satisfied. So this will imply that the Fm, the Hs omega, is basically the constant C times Fm. Okay, you have this compactness result. But here you can see Fm is bounded in L2, so therefore the whole thing is bounded by some constant. And this constant may depends on the sequence. But however, the sequence itself, they're close to Q. Okay, so it's bounded to C1, so therefore, so this constant can be chosen to be a uniform constant control the whole Hs law. Okay, so therefore you can see from here, then you can see that by the compactness, so you can see Fn will converge to some function f star. Yeah, right? Or is a subsequence. Well, may not be the sequence itself, it's maybe a subsequence. Now, if it is the case of subsequence, I just consider now a subsequence instead of the entire sequence. Okay? So now you can pass the limit. If you pass the limit, and this guy is actually not going to be 0 because the norm of this is always equal to 1. So you're not supposed to converge to 0 bound. Still having a unit bound. So now you can pass the limit from here. So you pass the limit, as n goes to infinity, you can have star Vn, so V1 and V2. 0. So because n goes to infinity in this part, what goes to V1, V2, as we did before. Okay. So here there's a two-step, The first step is once we define Fm, then we notice that this Fm is coming from this here, and this have the Vm1, Vm2 can be chosen to be any solutions. Okay, so this showing that because of that, so I will have a complex result. Okay, that's fine. And another thing is then we're going to choose the Vn, V2 more specifically by first choosing V1, V2. Then you use the boundary value to determine a special sequence here. Okay, so once this sequence is chosen, then I can pass the limit, and you can see that you are ending with this. So this will imply that the F star is equal to PQ2. Okay. So that will be a contradiction because PQ2 is complete. So how can you have a non-zero vector perpendicular to that? So that's the basic idea. And it's basically involved two steps in the calculus. So is there any other questions? So this result again is an intermediate. So this is an intermediate result. And this again is an intermediate result because it made an assumption then that this is complete. If this is complete, then you get uniqueness, right? Even though this is already tell us that give us the sufficient condition for the local uniqueness near a Q. They give a condition of Q, right? But whether such a Q exists or how much this Q exists, how many such a Q exists, still an open question. Okay. But here, before I move on, I want to make sure that you're okay with this. It's true. The main detail, the detail skipped is that showing this with that. Okay. That's follows on the regularity. Now, if there's no problem, then we can continue on the next target. Where we choose. Now, the next question is exactly how big is the set of potential for which this is complete. I'll give you an example first. So for Q equals 0, okay, then this P00 is complete. It is complete. Why? Because these are the set of, so in this case, this is just equal to what? It's the V1, V2, both V1, V2 are the harmonic complement. Right? Harmonic complement. And there I can choose V1 like equals to E C1x, V2 is equal to C2x with C1 dot C1 equal to C2 dot C2 equals 0, and also C1 plus C2. So these are complex vectors. IK. And then you can see that if f is equal to p00, so this will imply the integration of f to the product, right? E c1 plus e c2 x dx equals 0. So this means that this integration f e I to x dx equals 0 for all the k. But this one is just the Fourier transform of f. And the Fourier transform becomes 0, then the f itself is 0. So when q equals 0, I can verify this completeness and using these exponential, direct exponential solutions for the Laplace equation. But for non-zero q, then it is not easy to verify directly. Okay, so the question is, so if you just stop here, then it means nothing. But people will say, then show me a non-zero q for which it is complete. Right? So what the result here is that also you can define so the main result is that they exist O in C1 of the bar. So that's the space defining all the potentials, okay, defining the Q. So what is O? This is an open and dense set. Okay, it's an open dense set. Now here, so this is it's an open set in the sealed space, but also it is dense. We know what we mean by dense, right? Because any potential can be approximated by potential in this open set. Okay. Now, can you name an open dense set like for 2D space? It's very easy. Open set, but also at the same time it's a dense set. You just remove a line or you remove certain point, it's open dense set, right? Okay. So there's lots of open dense set. Okay. So there is an open dense set such that for any Q, potential is O, P, Q, Q is complete. So this set, okay, the potential which carry this completeness property is a pretty large set. Okay, that means besides a small set, it is almost every potential is carries such a property. So using this idea, the concatenate idea, finally you can prove that. But however, this is not the best result. It's not the best result. Because that actually the final result is that for any potential, no matter it is in O or not O, the PQQ is always complete. That's kind of it. But here, using this line of idea, this is the best you can achieve. Open dense set. Okay. Yeah. Okay, so again, so I'm not going to, so I just outline the details of about the proof. Okay. Okay, so what we're trying to do here is, so let's make some observation first, okay? Now, if f is perpendicular, so here, if f is perpendicular to QQ, okay, then this will imply that you have an identity f times v1, v2, dx equals 0, right? Okay, so that's the definition. But this, then I choose v1, v2 as the exponentially growing solution. That's a square solution. Then we'll end up with this. F e I k x 1 plus omega 1 plus omega 2 plus omega 1 omega 2 dx 0. Okay, so here omega 1, omega 2 I defined previously as the exponentially growing solutions, right? So so those are remembered for the exponential growing solution. So here, vi is equal to vci x and 1 plus 2. Okay, because everything is parameterized by k. So you can see, you can think about these are functions in k. Functions in x and k. Because k defines the c. Okay. So, but however, the integration is over x. So then you can see that after the integration, this integration still is a function of k. It's a function of k. Okay. Now without this remainder, this integration is just Fourier transform of f. Right. But here there's a one abstraction in continuous. You see this solution, okay, is x and k